Greetings, everyone. My name is Zixun Yu, and I'm from CS Department of Purdue University. In this talk, I'll present our work, Preemptive Text Warping to Prevent Appearance of Motion Blur. In our work, we propose a method to alter text imagery by warping the shape of letters, and the intention is to have the resulting imagery exhibiting minimized visual artifacts under preemptive motion deblurring. The method works for both camera-based and human-based observing. Motion blur is a problem that exists both camera-based and human eye-based capturing systems. For cameras, it occurs when cameras observe real-life objects in motion, and for humans, it occurs when they observe moving content on digital displays. In both cases, the motion blur can be simulated as convolution with a kernel of a box filter. The image on the left, convolved with the kernel, will produce this blurry image on the right. Pre-filtering methods pre-process the image before it is observed and with the motion blur. So here is an example of a pre-filtered image, and when it undergoes motion mechanisms with the same blur, and it will produce this blur pre-filtered image, which looks sharper than this naively blurred image, but it has artifacts or ringings. The problem of artifacts can be seen from the perspective of the frequency domain. We show the modulation transfer function of the box filter in the blue curve in this plot, and it shows that there are vertical dashed lines which indicate the frequencies on which the energy is almost killed. So if the target image has energy on those frequencies, then it cannot be reproduced no matter what the preprocessed image looks like. However, we found some images that are artifact-free when undergoing pre-filtering and then blurring, and then they shared the property that the foreground width is an integral multiple of the kernel size. And when we look into the frequency domain again, we can see that the 0 point of the image content is also the 0 point of the kernel. So there is no energy lost by convolving with the kernel. We give a name to images with such property called snappy, since the width of these content snaps to an integral multiple of some kernel size. This brings the main objective of our method, to change the shape of the target imagery so that it has no energy to be killed by the kernel. Notice that this work primarily works for solid color images like text. In order to have all foreground pieces at a width of integral multiples of a kernel, it mostly become a blocky shape. Triangular shapes and curvy shapes will have the width of a foreground piece varying gradually across different rows, so one could imagine that most of them are not snappy. Our method essentially places a rectilinear grid on top of the letters. Firstly, we place horizontal lines whenever number of intersections with the silhouette change. So the number of intersections change from 0 to 2 over here across this line, and changes from 2 to 4, 4 back to 2, and so on. In the next step, we place vertical lines that are spaced exactly k pixels apart, and these are the important step where we can define the blocks. Then we place blocks on the rectilinear grid. We replace each foreground segment of a horizontal slab with blocks of width k, and any adjacent blocks are merged. An optional step is to warp the rectangular blocks horizontally so that they look like the original curvy design. The top rectangle is stretched to a trapezoidal shape, like this. Some vertices from different quadrilaterals are supposed to be in the same place, respecting the original design. The green vertices here are the two examples. We adjust the placement of these vertices so that C0 continuity is maintained. The correspondence between rectangles and trapezoids allows us to interpolate between these two designs. We set t equal to 1 as the blocky design and t equal to 0 being the trapezoidal design. And any t between 0 and 1 determines where all these vertices of the quadrilaterals will be. We show 5 examples of this letter C, 5 different interpolants, from close to blocky design to close to original design. As far as human perception goes, different letters behave differently when they are geometrically interpolated. For letters that are already rectilinear, like E and T, the blocky design and original design will look similar. For triangular and curvy shapes, the blocky design and original design will look vastly different. We employ a machine learning-based method to determine the perceptual difference of any designed content with the original design. And with this metric, we can pick a desired perceptual difference, for example, this grade line, which in turn gives us the interpolant to warp every individual letter. Sometimes the kernel size is just too large to deal with. Imagine that one letter is 50 pixels wide and the kernel size is 25 pixels. And then in those cases, the previous method would have the letter unrecognizable. So we have to design them in a different way. For the common English alphabet and the numericals 0 to 9, 3 by 5 of resolution is enough to differentiate different letters. We take a 3 by 5 dot matrix design of these characters from some website, and they represent the lowest number of blocks needed to represent all these characters. So we have a 3 by 5 dot matrix design, and we take each dot from the design and replace it with a block of width k. It can be seen that the width of the letters needs to be 3 times as wide as the kernel for our design to work. But there is another compromise that we can make if the width of the letter is constrained but a larger kernel is present. The design can accommodate kernels of size up to half of the kernel. Single dot blocks on the side grows inwards to match the kernel size, and then blocks that had 2 consecutive blocks grows to the other side. However, the background parts are no longer snappy, so we call this foreground snappy. And of course, for a kernel size that is wider than half of the width, our design would just fail. All the design work in the previous step needs to be pre-filtered to counteract with the box filter. This is the minimization problem that we need to solve. We use Montalto's method, which allows for a trade-off between sharpness and artifact. A bigger theta value will drive towards a sharper image after blurring, but at a risk of having stronger artifacts. One last step before we show the pre-filtered image on the screen is to ensure that the pixel values are linearly mapped to irradiance emitted off the screen. Usually, it is sufficient to gamma encode the pixel values using the gamma value of the display. Now we show some results. We start by showing the letters in a very basic setting, original design, and it's pre-filtered and blurred, and then the snappy design with their pre-filtered and blurred version. In these close-ups, artifacts can be seen in the original design, but not in our warped snappy design. The amount of sharpness improvement is about the same. Now we compare our method with a few other schemes. Cornsweet illusion increases the contrast at the edges, but has similar blurriness compared to the one without any processing. Wiener deconvolution is a traditional method for pre-filtering, but it exhibits artifacts. Montalto's method is the one we use to pre-filter the image, and is also the method that we primarily compare with. Here we chose 3 letters to showcase the interpolation step of our design, the rectilinear shape, the triangular shape, and then curvy design. We chose the interpolants differently for each letter so that the perceptual difference to the original design is at these given levels. This image from the left is the pre-filtered image. The second one is the simulated blur result. And then we move the image on the screen by 1 pixel per frame on the monitor and use a camera to capture it. The shutter time is adjusted to the simulated blur. The capture image C and D kind of reproduces the simulated result, but we can also see that it's very important that we need to do color calibration. Our method also works for printed content. We printed the pre-filtered image and fix it onto the car, a toy car, and let it move across the field of a camera. The camera then captures a video, and then it shows that a pre-filtered image does appear sharp compared to non-filtered ones. We also conducted a user study to verify the effectiveness of our method in human vision system. The user is seated in front of a computer display, where the screen shows non-pre-filtered content and pre-filtered content at the same time, both in motion with the same speed, so with the same motion size. The contents are randomly chosen from 5 letters, or 5 of these letters, or simple vertical bars. For each content, there are 3 different speeds, and both snappy versions and non-snappy versions are shown, so 6 configurations in total for each content. And for each configuration, the users are asked 2 questions. Is the pre-filtered content sharper than the non-pre-filtered one? And how severe is the artifact? From the user's response, we can see that sharpness improvement is significant on medium and high speeds, but just no worse on low speeds. Snappy versions have better improvement than the non-snappy ones. For the artifact level, the snappy versions are overall lower than the non-snappy versions. So to conclude, we proposed a method to warp binary imagery for better preemptive deblurring. It does significantly reduce artifact levels, but the kernel size poses a limitation on the level of detail. For future work, we will work on general imagery other than just the text, and also we will work on real-time response to change in kernel size. That's the end of our talk. Thank you for your attention.